Good to be with you. You got the floor.
Good to see you guys. Let me share my screen here. And hopefully you can see the slides. Is that right?
Working correctly.
Okay. All right. So we're going to be thinking a little bit about our relationship to knowledge and certainty. We'll do a little math and physics if we can, but hopefully in a way that's accessible. So let me try to frame this a little bit. Some themes or some questions that we may hit as we go, and I'd welcome your thoughts on this as we go. In the context we're in, how should we think about knowledge? I find over the past, I don't know, 5 or 6 years, it's becoming harder for me to really ascertain what's true. And the degree of information, misinformation is significant, and the trying to find sources that are trustworthy is more difficult than it's been in my lifetime. So I've been thinking just about our relationship to knowledge, our relationship to certainty, in even the most foundational matters, in areas like math and physics. What's our relationship to being certain in these most basic of areas? I don't know if you think of math and physics as the most basic of areas, but that's the world that I'm in, and what's our relationship to certainty there? How
Only when I have to. Well, only when I have
to. What's the relationship to faith and certainty? How does the New Testament think about that relationship? And as we think through these issues, what ought our posture be in the world, and how does it relate to intellectual virtue? There are just some of the themes that we may hit on and speak to as we go. So let me start at least with the biblical text. We're going to do some physics today, but let me begin with getting our head in Scripture. So just some places in the New Testament where you see these themes come up. One is in Hebrews. Faith is the assurance of things hoped for, the conviction of things not seen. The context of that text in Hebrews is persecution of the church and perseverance that the author of Hebrews is calling that community to, perseverance in the face of that persecution. And you see a kind of contrast between faith and hope and that which is seen there. Another is in Romans, for in this hope we were saved. Now hope that is seen is not hope. For who hopes for what he sees? But if we hope for what we do not see, we wait for it with patience. Again, you're seeing a kind of I don't know if tension or contrast that's being brought out between hope and what's seen, what's hoped for and what's seen, the objects of hope and the objects of what's seen. And again, patience, or if you like, perseverance. So in both the Hebrews text and the Romans text, there's this kind of eschatological focus or attention there, that we're waiting for the return of Christ. And the third of these that I was just going to bring up, for this light momentary affliction is preparing us for an eternal weight of glory beyond all comparison, as we look not to the things that are seen, but to the things that are unseen. For the things that are seen are transient, but the things that are unseen are eternal. Again, contrast between what we see and what we don't see, faith and sight. And again, in this text, you see this relationship between that tension and our momentary affliction, persecution, and looking forward to something that is to come, something better. These are just some of the observations that I draw.
Hey, Walt, can I ask a question?
Please.
As I read these, one of the things that I always think about is seeing is only talking about one sense. And when you think about all the other senses, because some things you hear, some things you can feel, taking it to senses as opposed to seeing, taking it too far?
No, I think that's helpful. We're going to come back to this in a couple weeks in a little more detail. But yeah, I think that's a helpful thought. That which we take in through our senses, if you like, can I use the word empirically, versus that which we can't take in from the senses. Those truths and realities that transcend our senses or our observation. I think that's probably helpful. And with respect to those things that we take in that way, what do we actually know about what's seen? And again, we want to think about this in the most fundamental level. So we're going to start today thinking about this in the context of physics, and then the next week we'll think about this in the context of pure mathematics. And so let me give some caveats. The first of all, a caveat I want to give you is that when we're talking about physics, we're going to talk a little bit about quantum mechanics. Keep breathing in through the nose, out through the mouth. Find your happy place. You're among friends. But whenever the problem is, here's the bad news. The bad news is the closer you get to the math with respect to quantum mechanics, the clearer things get. That's the bad news. The good news is I'm going to try to do this without putting a single equation in front of you. That's my goal. So no equations if we can help it. We'll try to use as ordinary language as we can. But when you're talking about some of these things that are extraordinary, sometimes the ordinary language falls short. So let's just all keep in mind we're among friends. Most of us aren't math and physics geeks, so as the concepts get hard and difficult, you'll ask questions and you'll interrupt me, right? So please don't hesitate to do that. So let me give you a little history. Let's back up a little bit. I'll pick up the story in the 1600s, late 1600s, when Newton is doing Newtonian mechanics. That's sort of talking about a theory of gravity as force that acts on objects. Newton also did calculus too, right? He used calculus to do this. But Newtonian mechanics, really, really effective, essentially got us to the moon for the most part, was Newtonian mechanics. The next, I don't know if I'd call it a revolution, but Laplace sort of thinks about gravity as a field, this field that we sit in that's acting at every point in space, and having values at each point. So the further you get away from a massive object like the Earth, the weaker gravity becomes. That's called the inverse square law. The next sort of relevant move that's made is Maxwell's theory of electromagnetism, right? So he's thinking about forces related to electricity and magnets, and he's able to describe them in one theory that is known now as E&M, or electromagnetism. It also explains the nature of light. So it understands light and electromagnetism as a wave that propagates through space. And so I wore my Maxwell's equation shirt today with now I don't think I'm only bringing you the best stuff, right? I know Tim talked about the Lord's Prayer. I'm pretty sure he didn't wear a Lord's Prayer shirt for his presentation, and I don't think Carrie wore a Nicene Creed shirt. So you're really only getting the best from me. But these are Maxwell's equations, and by the end of the 1800s, people were so confident in the scope of physics, and it was so effective at describing the world, that senior physicists were telling students, you really shouldn't go into physics because all the work is done. The problems are all solved. And then the 20th century happened, and lots of things changed. People understood that wasn't the case. Still in the classical context, though, I'll just bring up Rutherford and Bohr. And what Rutherford and Bohr are important is they discovered, I don't know if discovered is the right word, but they described the atomic nucleus. So they described atoms as a nucleus made of protons, which are positively charged, and neutrons, with electrons that are negatively charged that would orbit the nucleus, right? So you've all seen sort of pictures of atoms where they're like little solar systems, and you've got the nucleus with electrons sort of going around in orbits like that. That's what Rutherford and Bohr discovered. And even when they were talking about this and giving sort of describing this theory, Bohr was a little skeptical that it was quite right. It turns out it's not quite right. It turns out that that's not really what atoms look like. And it's in the 20th century that you start to see some cracks in Newtonian mechanics and in classical physics. Some areas where those theories aren't quite working, right? So Newtonian mechanics works really well when you're talking about everyday things like baseballs and automobiles and even rocket ships.
Question, well, before you go,
Yeah.
and I'm not sure if this is framing it the right way, but in what ways were each of these, um, each of these men's, work or discoveries, was it, um, building on the knowledge of Newton and others like that, or was it saying, no, they had it wrong, this is a more accurate or a right way to look at it?
Yeah, so far in the story, I would say they're building on, right? They're making advancements, but I don't think anybody thought there was anything inferior about what Newton's mechanics, right? So everybody thought Newton's mechanics was right on the money, and it described the universe perfectly, and it described gravity in particular, but it didn't describe electromagnetic waves. But even when you study electromagnetic waves, Newtonian mechanics still works very well there, right? So I would say they're building upon but not contradicting. And it's not until you get to the 20th century where you get Einstein thinking about relativity, which we won't be focusing on, and um, some of these figures in this slide that we'll talk about, and they're looking at things that are very small, right? They're looking at the atomic level. And Newtonian mechanics, this is where it fails. This is where it's not working. And there are two places where this is seen. One is with black body radiation. A black body is just think of a perfectly black object that gets heated. And when you heat a black object, so there's no light that's reflecting off a perfectly black object. But as you heat this thing, electromagnetic waves are coming off. So you can imagine heating something that's black and it turns literally white hot, right? It might glow orange and then it might glow white, not because light is reflecting off of it, but because that heat is coming off in the form of these electromagnetic waves. And what they discovered was, again, you hear me using the word waves. What they discovered was that these waves, the energy of these waves coming off of this black body, came in discrete packets. So when you think of a wave propagating through water, for example, you drop a pebble in water and the waves propagate out. That's a continuous phenomenon, right? The waves are smooth and continuous, right? And what they were finding with the black body radiation is that what was being emitted was coming off in discrete packets of energy that depended on the frequency rather than a continuous distribution that you'd expect. That is, the waves of radiation acted like particles. They didn't act like waves. So this was the first hint that there was something wrong with the picture of the world that we were looking at that level. So the first was waves were acting like particles in discrete packets of energy. And then the second one, and we'll spend a little more time talking about this, is what's known as the double slit experiment. So I'll show you this with a slide. So imagine what you've got on the left there is a beam of light, say a laser beam. And then you've got a surface with two small slits in it. And the light hits that surface and those two small slits, and then the light gets split and is going through those two slits. And as the waves of light go through those two slits, you get what's called an interference pattern. So you can imagine if you have two pebbles that you drop in the water and the waves are propagating, the peaks of the two waves are going to combine and make very high peaks. And the peak of one wave in certain places is going to meet the trough of the other wave, and they'll cancel each other out. That's called an interference pattern. Where two peaks combine, you get a very high peak, and where a peak and a trough combine, you get essentially no disturbance at all. And so when these waves would hit a screen, you would see that interference pattern, right? Where it's very bright in certain places and then dimmer in other places where you get that cancellation. So no news there. That's how waves work. So light we understood as traveling in waves, and that's what you would expect from waves, right? You would expect that in propagating water, you would expect that in light. No news there. But what they found was when they fired beams of particles, beams of electrons in the same context, what you would expect to see is the electrons that made it through the slits would hit this detecting screen and would show up in two clusters. The cluster from the first slit and the cluster from the second slit. Again, these aren't waves, these are particles. Think of them as like BBs being shot or bullets that are hitting the screen. That's what you would expect. But what in fact happened when you shoot electrons at these two slits, you got this wave interference pattern. So they gathered not just in two clusters, one for each slit, but rather in these peaks and kind of valleys, the way you would expect to see waves happening. You get an interference pattern with particles. Again, this is an example of particles acting like waves, right? So in the case of the black body radiation, you get waves acting like particles. And in the case of the two slit experiment, you get particles acting like waves. And no one quite understood how to account for this. It didn't make sense. By the way, it's not that the beams of particles were going through the slits and interacting with one another in a certain way and causing this. If this happens, you see the same behavior if you shoot an electron through one at a time. After one at a time you fire it, it hits the screen. Another one you fire it, it hits the screen. You do this for enough time and you get the same interference pattern. It's as if a single electron is going through the two slits and interfering with itself like a wave would. And this was confusing to everybody. Nobody quite understood what to do with this. And it gets weirder. Suppose this time you're doing it with these particles and there's a detector that's there. So Tim is looking at one of the slits and he's looking at the slits and Tim is seeing if a particular electron goes through this slit or it doesn't. So an electron's going through and he's looking at one of the slits and he can tell if the electron goes through the first slit or the second. When he is watching, when there is an observer or a detector, you get no interference pattern. You get what you would expect. So again, you run the experiment with an observer or a detector, and you get two clusters of particles, exactly what you would expect. But when you take the detector away, when Tim isn't looking, you get the wave interference pattern. It's almost as if the electron knows you're looking, and when you're looking, it acts like a particle. And when you're not looking at the slits, to see which slit it goes through. It acts like a wave. You'll hear people say that it's going through two slits at once. That's a little misleading. It's not going through two slits at once. It's just acting like a wave when it's not being detected, right? Again, very strange, very confusing. And people were trying to sort out what's going on there. I'm sorry, go ahead.
If you're not watching, how do you know what happens?
So you don't, when you're not watching the slits, you don't know which slit the electron goes through. But when it hits the screen, when it hits the screen, it's going to leave a dot on the screen. So you know that it's hitting the screen, but you don't know which slit it's going through. So the observer or the detector is watching this I don't know what we would call it, this thing that the electrons can't go through unless it's going through the slits. You know, maybe it's a rod or something, or a wood that the electrons aren't going through. So that you know what's happening. You can see what's happening when they hit the screen. But if there's somebody looking at this part where the slits are, then it acts differently than it does when you're not looking at that, which is really puzzling. Like, so if you're confused, that's right where you should be. That's everybody was confused.
So is you're moving towards some conclusion, but is there some sense that the particles, like your heading is, doesn't know we're looking? That seems to assume or ascribe a certain level of awareness or knowledge or
no, that's just there to be provocative, really. No, I don't. But that's what people wondered. And by the way, people do draw conclusions about that. I don't hear physicists drawing conclusions like that, but it does. That's sort of what it seems like. If the electron knows you're looking and it's going to act one way, and if you're not looking, it's going to act another way. But I'm just being provocative there. That's not really what the physics would say. So what's happening here? Well, the issue is that the physicists don't really agree or know what an electron is. So we think of an electron maybe like a little marble, right? Like a particle. But what we're seeing in this experiment is that sometimes it acts like that, and sometimes it acts like something else. It acts like a wave, right? What really is its nature? And the answer is, physicists, if you go to a physicist and you ask, they might say, we don't quite know. Sometimes it's described as there's an electron field, and the electron itself is a vibration in that field. But the kind of being that an electron has, physicists don't really know, or they don't really agree necessarily. And so things like electrons or protons or neutrons or photons, which are the particles associated with light, are modeled by something called a wave function. And that's what this Greek letter phi is. And so the way physicists think about it is, you could think of a coin that sits on a table. Now, a coin that's sitting on a table is in one of two states, heads or tails. That's how a coin would be, right, if it's sitting on a table. And similarly, we'd expect an electron to be in one of any particular position. But unlike a coin, the way physicists think of an electron is the electron doesn't have a position when it's not being observed. It's in what's called a superposition. It's as if the coin, if you're not looking at the coin, it's as if the coin could be in heads or tails or some combination of both. Likewise, the way physicists would understand the electron is its position isn't determined when we're not looking at it. It's in a superposition. Does it even have a position? Does it even have a place? Again, if you think of the electron like a marble, the marble, even if we're not looking at it, is in a particular place in space. It's in a particular spot. And physicists are saying, no, that's not what's happening. When we're not looking at the electron, it's not in a particular place. In fact, even that language might be misleading, that it has a location, right? But then when you measure it, its position gets determined. It has a location when it's measured, when you have an observer, right? Again, this should be very confusing, right? You should be thinking, I don't know what's going on here, right? It's mysterious. And the way physicists talk about this, this wave function phi or psi, excuse me, is modeled probabilistically. So a physicist would say, okay, we can't say precisely where the electron is, but we can say with a certain probability that it's in this region. And it turns out that this is called the standard model. The standard model is extremely effective. So I said that Newtonian mechanics got us to the moon and back, right? Very, very effective theory. Quantum mechanics, which is what we're describing now, has been described as the most effective scientific theory that has ever been devised. So, as mysterious as all of this quantum behavior is, as mysterious as it is extremely effective at what it does. These probabilities work very, very, very well. Again, it's described as the most effective physical theory or the most effective scientific theory in history, even more so than Newtonian mechanics, which got us to the moon, which is kind of striking. So on one hand, it works really well. On the other hand, there's a lot of mystery surrounding it, right? There's a lot of mystery in saying, well, what is an electron? Is it a wave? Is it a particle? Is it something else? Does it make sense to talk about its position, right? So some physicists will talk about its position, some physicists won't. There's a lot of mystery surrounding it. And I'm just looking at the clock and I'm a little worried. I should probably start to wind us down here. But the point that you want to take from this is,
I've got another question, Walt.
yeah,
So the electron or proton, when it's observed, takes on a certain location or characteristic. If there's more than one observer, will the particle have a consistent, I don't even know,
position.
place or something like that? Or if I'm looking at it and then I look away and then you look at it, are we going to see two different things?
No, there's this consistency from observer to observer. Yes, that's there. So yeah, no, you're going to see that. That's why it's so effective. It works really well. But when there's no observer, it turns out I have some. I don't have time to get into it in detail, but it turns out that there's this complementarity that's going on. If you know the particle's position, you can't know its velocity. So the more accurately you know its position, the less accurately you know its velocity. And conversely, the more accurately you know its velocity, the less accurately you know its position. This is the only place in the universe where this kind of thing happens, is with these quantum objects. A baseball, we could say with certainty that it's in this location and it's moving at that speed. It's not how it works with electrons. If we know its location, we don't know its speed. And if we know its speed, we don't know its location. So there's a hard limit on, and it's not because we just don't have enough information. It's the nature of quantum objects. It's not like if we had better detectors, we could figure this out. It's not like technology is going to get us out of this thing. It's inherent in the mathematics that you can't know both of these things simultaneously. The better you know one, the less you know the other. This is known as what's called the collapse of the wave function and Heisenberg's uncertainty principle. And so for us, the takeaway is that there's this getting back to the theme we want to think about, faith versus sight, in terms of what we know physically about the most basic fundamental things in the universe, the things that all of the things in the physical universe are made of, atoms, electrons, protons, neutrons, there's a lot of uncertainty built in that we can't get around with respect to these things. And so even the things that we can see, we can't see with a kind of certainty. So I should probably stop and let you guys ask some questions about this, because I'm sure I've managed to confuse you pretty well.
If you look at the conversation we're having about physics, you've got the double slit experiment. Those electrons are going through slits, which are basically atoms on either side, like two slits of metal, atoms on the outer layer. So those electrons are interfering with the electrons in those slits. It's not just two slits that you're dealing with. And so if they had logic in the way they analyze these sort of experiments and reason, they would come to different conclusions, that it's not such a wackadoodle system. So for example, when the electrons go through there, they have a certain velocity, which means they have a time delay in the relativistic perspective, and with respect to the electrons in those slits. And what happens is those electrons actually interfere with the electrons in the slits. It's not the slits that are apart. So if they analyze it logically, what they do is, like, when you have like an electron, you have something called a positron, which is the antimatter particle. When those two little beasties get together, they annihilate, they form two gamma rays that go off in opposite directions. So energy and matter exchange. And what they're missing is the relativistic perspective, because when that electron has a slower time frequency as it's going through that slit, that ends up changing the speed of the clock of that electron. And these electrons have a fundamental frequency to them, which is that frequency of the gamma ray that gets created when they annihilate. So if you think of an electron as a particle with a fundamental frequency, you give it that fundamental frequency, you reduce that frequency a little bit by the time thing, and then you can see the interference pattern that comes out in that double slit, which is actually, it's actually is what's showing up is that interference pattern, and you can calculate it by something which is called a beat frequency. Like if you tune a guitar, you're trying to get everything in tune, and one of those strings is just a little bit off, it's not tight, you see something called a beat frequency. So what these beat frequencies are something that they call de Broglie waves. De Broglie waves are supposed to explain like why you can only have discrete energy levels in the electrons that go around orbits. So if they did a systematic analysis of what's really going on, instead of this arbitrary, oh yeah, it's the electrons interfering with each other, and they looked at the real physics of the model that's going on, they could see the underlying physics that unites relativistic mechanics and quantum mechanics. And when you get de Broglie waves coming out of a system that's being explained by relativity, you have a united perspective on the system. So what's missing is that perspective, and we come up with all these physical things like trying to describe quantum mechanics with strange words instead of the actual physical reality of what's producing them. So I think it's just frustrating, because when you try to explain physics with a limited model like this, they don't look and analyze the reality of what's actually going on and come up with the real conclusions, which shows how God created a universe that actually interacts with each other logically and just works. And I find it frustrating that we have to use words to describe things, and I think that's the frustration of physicists trying to describe what's going on. So, I mean, I've studied all this stuff as an electrical engineer and things like that, and the science is extremely important. Like, and why it's important as a Christian is because you see, essentially, like, we're starting to discover some of the underlying physics of our current universe. We haven't perceived this because we have better views using like beyond the Huddell telescope, the Webb telescope and stuff, to see what's going on in galaxies. And they can rationalize what's going on from a cosmological, relativistic perspective on how all the astrological bodies behave. And what's important is that the quality and the nature of our reality in this world was something with all these fine-tuned constants by God that would not allow for carbon, oxygen to interact, the different elements in order to make, the organic molecules that were made up. We wouldn't have life in the universe. We wouldn't have this beautiful universe that works to create life in all humanity.
So I'm not sure where you're going, but I'm not sure if there's a
Oh, that's
question
fine.
or some kind of dialogue between you and Walt that would be helpful.
Yeah, so I think what Walt is saying is like, there's like a fine-tuned constant to the universe which shows up to explain these divergent views that allows our universe to work. And as Christians, we can understand this physics only works because of the unique properties that God has given this universe so that it works out to create life. And that's what's important about all the physics stuff, because you have the Bible as the book of evidence of God, and then you have the physical reality of how our universe works, and that's evidence of God because it was divinely created with certain properties that wouldn't be there if God wasn't there.
Well,
Yeah, so certainly no argument there that God has set up the universe perfectly for us to be in and have dominion over, I think is, and that his design and the wonder that we see as we observe it is uh, just striking and breathtaking, that you see. But I can assure you that the quantum mechanics we're describing here is the real physics. It's it's the this there's the Heisenberg's uncertainty principle and wave particle duality. These are not controversial matters. Now what the nature of these things are, what an electron really is, that's something that there's two kind of ways to interpret this. One is the many worlds interpretation that we don't really have time to get into, but most physicists sort of take what's called the shut up and calculate interpretation, or the Copenhagen interpretation. And what we mean by that is what most physicists are doing is, okay, we have the wave function and the Schrodinger equation, and they're very good at making predictions, which is what physics is supposed to do. I have a theory, I apply the theory to the world, I do experiments to see if that matches. And the wave function and the quantum mechanics as it developed in the 20s and the 30s is remarkably good at that. And it's not controversial, right? What physicists don't, one of the things that physicists don't know is how to unite quantum mechanics and relativity, right? So all of the things I've been describing have been non-relativistic phenomenon. We're not, the velocity of electrons is such that there's no relativistic effects taking place there. So we really don't have time to get into the weeds on the physics, but I can tell you that that most of the quantum mechanics we're describing here is uncontroversial, and it's the standard understanding in physics now, and has been for 100 years.
Well, I love your field, and I know nothing about it, unlike my brethren sitting next to me who knows a lot about it, but I know people, and so you guys start really in 1911 with the Solvay conferences.
Yep.
The physicist Solvay conferences by invitation only. Madame Curie, you're the only woman there, with Albert Einstein standing behind you, and there you are. They're all the men born in the 1850s that are the scientists, and then on it goes with you guys, with those conferences, those Solvay conferences, with your physicists. Now, my understanding is, as it relates to your group, there's a high expectation that you will be Christians, guys, in your studies, that you guys will actually believe in Jesus Christ. That will make a lot of sense in your brain for some of you. I will find out when I get up there, Walt, who's up there, of those scientists, because I'm tracking them like a dog, even though I know nothing about what they study. Well, I know nothing about all what you just said. I know nothing about that. However, with what you studied of the universe, many of your colleagues were Christians, and of those photos that I had, it's like pinup girls. These guys are my pinup girls.
Yeah.
And there you go. You ever think you'd be a pinup girl, Walt? I mean, come on.
I don't know. That picture from the Solvay conference that's sort of famous. Depends on the circles you run in, but it's sort of famous. There has not been a group of scientists that have been that influential, I don't think, together since. I don't know, the Babe Ruth and Lou Gehrig Yankees, maybe that's what that picture looks like. It's Einstein and it's Planck and it's Bohr and it's Heisenberg and all the rock stars. We haven't matched it since.
So question, Walt, you said when you were kind of taking us through from Newton on that, the knowledge that Newton was able to, to gain, led to, being able to put a person on the moon, and the knowledge of atoms and atomic energy and stuff like that allows us to create electricity and, bomb the hell out of cities and things like that. Is there any sense of where this, quantum level of physics might have an application?
Oh, it's used all over the place in computer chips, electrical engineering, and anything that has to do with sort of what's going on at the Large Hadron Collider and particle physics. So the issue is that what you don't need it. All these quantum effects, sort of, quantum theory applies to the macroscopic world. It's just that quantum theory aligns with Newtonian mechanics at that level. So when we're talking about baseballs, quantum theory and Newtonian mechanics are the same. They're making the same predictions. The issue is that when you get to the very small things, protons, electrons, photons, things like that, Newtonian mechanics fails and quantum mechanics works. On the other hand, when you get to the relativistic world, so relativity is on the other end of this, relativity and Newtonian mechanics also align when we're talking about baseballs. But when you're talking about things that are traveling very, very fast, or really significant gravitational forces like in black holes, in that case, relativity works and Newtonian mechanics fails. So you have relativity at this end and quantum mechanics at this end. The only thing that works here is relativity. The only thing that works here is quantum mechanics. And then in the middle, you have Newtonian mechanics, and relativity and quantum mechanics and Newtonian mechanics all work well for things like baseballs. But for protons, only quantum mechanics works. And for black holes, only relativity works. And so what physicists want to do is develop a grand unified theory that unites relativity and quantum mechanics. That's what the leading edge of physics is working on, and has been for 40 years without much success. But that's what the string theorists are really trying to do, is unite gravity and quantum mechanics.
So I'll make two requests. One is, if you want to give us a preview of next week, you're welcome to, but if you want us to come in surprise and surprise us, that's your call. And then if you would close us in prayer as well. So
yeah, so I'm not a physicist. I mean, I know some physics. The application of my math is physics. But next week we're going to talk about math. We're going to talk about what mathematicians look at versus what physicists are going to look at. But we're going to draw a similar kind of conclusion, that in the same way that there's a hard limit on what we can know in physics, we're going to see there's a hard limit on what we can know in mathematics. So that's sort of the preview. And we want to think about that as, again, in terms of our posture in the world. Maybe the word humility is useful in this context. There's a hard limit on what we can know and be certain about. And we'll talk about that in a mathematical context next week. And then in 2 weeks, we'll sort of try to bring this back to the New Testament and think about what it says about faith versus sight. But yeah, I'll pray for us.
Thank you.
Lord, the more we look at the world and that which you've made, the more wondrous the Creator who made it becomes to us. And we're left sort of speechless with how to approach you, how to understand you. So we just thank you for the wonders that you've made, and in particularly for the gospel that gives us access to that Creator. We thank you for the work that Christ did for our sake, and help us to see you more effectively, and may this wonder affect the way we worship on Sundays and throughout the week. We ask it in the name of Christ. Amen.
Man,
Amen.
thank you, Walt.
Thank you all.
Yeah.
Thanks, guys.
Wonder is a good word there, yep. Okay. Dave, Frank said
I'm gonna shut it down.
handle that, so, good.
See you next week.
Yep, yep.
That's cool. So I hang out some Sundays with a guy named Jeff Jewett, and he was the soccer coach for Shipley, as well as the soccer coach for Devon Prep. I think Devon Prep or Malvern. I can't think it was Devon Prep. Great soccer coach.